Chapter 20. More about tests and intervals. Zero in on the null. The appropriate null arises directly from the problem. Think about why the study is being done and what we hope to learn from the test. The null hypothesis is the starting point. It assumes nothing has changed. The alternative hypothesis, all other values of the parameter that we would consider plausible if the null is rejected, can be expressed as greater than, less than, or not equal to. How to think about p-values. The probability of getting results at least as unusual as the observed statistic given the null hypothesis is true. The p-value is not the probability that the null hypothesis is true. What do we do with a small p-value? Well, a small p-value means that a result like the one we observed is unlikely to occur if the null hypothesis is true. And the p-value is a measure of the strength of the evidence against the null hypothesis. A smaller p-value implies strong evidence against the null hypothesis. What do we do with a high p-value? Well, what we have observed is not surprising. The results are consistent with the assumption that the null hypothesis models the world. We have no reason to reject the null. It does not prove the null hypothesis is true, but offers no evidence that it is not true. So remember, we are rejecting the null when we have a low p-value. We do not reject the null when we have a high p-value. An alpha level is an arbitrary threshold set before collecting data. If the p-value is less than alpha, then reject the null hypothesis. The result is statistically significant. Now, the common alpha values are 0.10, 0.05, 0.01, and 0.001. The alpha is also called the significance level. So practical versus statistical significance. So the effect size is the difference between the value you see in your data and the null value. It's a good idea to include a confidence interval with your hypothesis test. Now, the confidence interval is centered on the observed effect and puts bounds on how big or small the effect size may actually be. Confidence intervals and hypotheses test. Now let's take a look at the notation that we use for each of these. So for confidence intervals, we use the standard error of p hat. That equals the square root of p hat times q hat divided by n. We also use the margin of error, which is your z-score times the standard error of your p-hat. And the interval is the p-hat plus or minus your margin of error. Now for the hypothesis test, we use the standard deviation of p-hat. That's equal to the square root of p-naught times q-naught divided by n. And the z is equal to p-hat minus p-naught divided by the standard deviation of p-hat. Now, it is possible to make an error when you're doing a hypothesis test. So a type 1 error happens when the null hypothesis is true, but we reject it. That's also called a false positive. A type 2 error, the null hypothesis is false, but we do not reject it. That's known as a false negative. The alpha level is the probability that a type 1 error is made. Now I have the same information down here below in a table where I have my decision versus the truth. So if my decision is to reject the null and the null is true, I've made a type 1 error. If my decision is to reject the null and the null is false, then I'm okay. If my decision is to not reject the null and the null is true, then I'm okay. If my decision is to not reject the null and the null is false, then I've performed a type 2 error. So the power of a hypothesis test is the probability of rejecting a null hypothesis that is actually false. The power of the test is greater when any of the following is true. The significance level is greater. This also leads to a greater chance of a type 1 error, though. The effect size is greater. Well, the farther from the null the truth actually is, the easier it is to detect. The sample size. Larger sample sizes lead to greater power. The amount of unexplained variability. Reducing variability increases the power of the test. Let's look at an example of type 1 and type 2 errors. So last year, a survey found that 45% of a company's employees were willing to pay for on-site daycare. The company wants to know if that has changed. So our hypotheses are the null p equals 0.45, because remember, the null is our hypothesis that claims nothing has changed. Okay, so the 0.45 relates back to the 45%. Nothing's changed, it's still the same. Our alternative hypothesis, p is not equal to 0.45. And the reason that we used a not equal to is because the company's question is, did that number change? They just want to know if the new number is different than 45%. They're not asking if it's specifically decreased or increased. They're just asking, is it different? So therefore, that's going to give us a not equal to, which would be a two-tailed test. P is the proportion of company employees willing to pay for on-site daycare. So what happens if we make a type 1 error in this case? Well, if we make a type 1 error, we would be rejecting a true null. So we would be concluding that the proportion of employees is not 45%, when indeed it is. What would happen if we made a type 2 error? Well, in that case, we do not reject a false null. So we would conclude that the proportion of employees is 45%, when indeed it is not 45%.